welcome back. So, in the last class, we have seen our discussion on DAB, where initially we have started with our simplified circuit, where we were assuming that the output stage was short circuited, then we have gone to actual loading, then we have seen what happens to the operation of DAB when we have difference in the rated voltages. Okay, so if the rated voltage is not connected at one of the terminals, what will be the effect on the DAB operation? We have seen that the charging and discharging will be done throughout the 4 modes of operation, whereas when the nominal voltages are connected across the terminals of your DAB, we have seen that charging and discharging will be done in mode 1 and mode 3, and 2 and 4 will be maintaining the currents which was left after mode 1 and mode 3. Whereas when we have difference in the voltage, we have seen that it will be charging for mode 1 and mode 2, and it will be discharging for mode 3 and mode 4. We have seen the expression also how the power flow will be controlled. So, when the angle is between 0 to 180 degree, the power flow was positive. When it was between 180 to 360 degree, the power flow was negative. It was maximum positive at 90 and maximum negative at 270 degrees or minus 90 degrees. So, we have discussed the first method of operation of your DAB, that was our single phase shift control technique, where we assume the bridges to be operated with and generating square waves which will be phase shifted by an angle of delta. Okay. What was the operation of the other devices? That is, we have considered S1 and S4, those were our diagonal switches as one pair, and the other pair was S2 and S3, the other two diagonal switches in one bridge. Same way we have operated the other bridge also, S5 to S8. There was a shift between S1 and S4 pulse and the S5 and S8 pulse, which was the positive switches of both the bridges. We have seen that there will be a phase shift of delta. By changing this delta, we were able to regulate the power flow. We have also seen what will be the meaning of the back power or the reactive power in this circuit. Because of this back power, we will unnecessarily create some amount of additional current in the circuit, which will increase the loss in the circuit. So, when I talk about the degrees of freedom, okay, so it will have single phase shift control will have 1 degree of freedom, that is the shift between our primary and secondary voltage, which is marked as delta. Okay. So, by changing delta, what I am doing indirectly, I am creating the phase shift between V1 and V2, and we have seen the equivalent circuit of our DAB also, where we will have square wave, 2 square waves separated by an inductor, which will be our leakage inductance of the transformer or an external inductor. Okay. So, because of this shift delta, we were able to control the power flow in both the directions. Okay. So, once my DAB is designed, I cannot change the value of L or any other parameter, only one control parameter is left with me, which can be changed as per my requirement, that is delta, or the phase shift between the primary and secondary voltage. So, that is why it is called as single phase shift control technique. So, what are the demerits and advantages of this circuit? So, first let us see the advantages. So, it will allow us bidirectional power flow, and it is the simplest among the other methods, which we will be seeing next. We will see that this will be the simplest one. It is very easy to realize. We have only one variable, that is delta. Based on that, we can easily draw the gate pulses, or the controller can be easily designed. Demerits: it suffers from high circulating current, and it has only 1 degree of freedom. Okay. So, what is the meaning of circulating current? The current which will be flowing during the back power mode, that is called as circulating current, because they are not participating in the power transfer. Here we have only 1 degree of freedom, that is our delta, that is the phase shift between primary and secondary bridge. Okay. So, what is the importance of this degrees of freedom? So, now as I said, this circulating current, suppose I want an circuit which has minimum circulating current and which has capability of controlling the power flow also. So, in this case, can I do both of this by using a single degree of freedom? The answer is no. Either I have to go for optimization, where none of them will be completely addressed. I can have an intermediate solution, or if I want to have particular solutions of 2 items, that is, I want to precisely control the power flow as well as I want to regulate the circulating current, suppose. So, I will be requiring 2 degrees of freedom, which is not possible over here. Okay. So, although this is the simplest method, it has bidirectional power flow control capacity, but it will not be able to do any associated or add-on task, control task, if required for the applications. Okay. The other thing is soft switching. Okay. So, what do you mean by soft switching? So, in this DAB circuit, if the incoming switch, suppose we consider the switch S1. Okay. So, what do we mean by soft switching of this one? Okay. So, the other important parameter which we generally consider in the control circuit design, that is, first will be our circulating current should be as minimum as possible. We do not want circulating current in the circuit. The power flow should be bidirectional and we should have precise control on the power flow. So, that will require 1 degree of freedom at least. Then we required one more additional thing, that is soft switching. Okay. So, what is soft switching? Till now we were not discussing about the losses in the circuit. Okay. What we have assumed till now, if this is the voltage, this is the current, when the switch is off, it opposes rated voltage. When it is given the gate pulse, it carries the rated current, assuming the voltage and currents are perfectly DC. So, here this is the transition period where the gate signal was provided. So, from the blocking state, the switch goes into the conduction mode and it is almost instantaneous. So, if I calculate the loss in the circuit by multiplying the voltage and current through the device, I will see that the power loss will be equal to 0. Okay. So, this is the idealized circuit, but in the real case we will see that the voltage will have a slopey nature, it will not drop instantaneously and the current will be slowly picking up instead of going to the nominal steady state value instantaneously. So, we will have an common area. Okay. So, when I calculate the power loss in this circuit, I will see that there is a finite duration where both voltage and currents are finite. So, we will get some power loss over here. Due to this, the product of this one will be giving me the power loss component. Okay. So, it will not be equal to 0, we will have some type of loss in the circuit. Now, this is your normal switching or hard switching. If I want to go for soft switching, okay. So, what can be the options? I have to make any one of these two parameters 0 prior to the switching instant. If I make the voltage as 0 across the device prior to the switching instant, irrespective of the delay in the current, voltage is 0. So, the power loss will be 0. Similarly, if I ensure that the current will be 0 before the turn on or turn off transition, so irrespective of the voltage drop time or rise time, it will not affect the power loss in the circuit or the power loss will be 0. So, generally we try to maintain ZBS switching for our DAB circuit. So, how that can be done? That can be ensured ZBS switching or 0 voltage switching if this diode comes into conduction prior to the switching of this circuit. Okay. Suppose I am turning on this switch S1. Before the conduction of S1, if I ensure that the current is flowing through the antiparallel diode, so the diode will be in the conducting state. So, the on state drop of this diode will be applied across the switch, which will be around 0.5 to 0.7 volts, which is nothing compared to the supply voltage, which will be around 400 or 800 as per the application. So, here if the diode comes into conduction path, the S1 will see near 0 voltage, so it will go into soft switching mode. So, as our switching frequency is very high, the switching losses of these circuits will be dominating over here. Okay. So, the maximum part will be contributed from the switching loss in the circuit. So, if I am able to go for soft switching, I will be able to increase the efficiency of the circuit. Okay. So, ZBS range will also be dependent on the control technique which we are using. Here we do not have any flexibility or any degree of freedom left with us to improve our ZBS operation range or to expand our ZBS operation principle. Okay. So, here, so this is the requirement of our degrees of freedom. So, we have seen three such requirements. First is if I want to minimize the circulating current, the default requirement is the power flow. I want to control the power flow if I want to have ZBS and so on. So, if I want to control all these parameters independently, I will be requiring more and more degrees of freedom. Whereas, in this case, we have got only 1 degree of freedom. So, that is what is the main limitation of our single phase shift control technique. Okay. So, now let us see what are the other methods of controlling your DAB. The next one is your extended phase shift control technique. Okay. So, here if you see, instead of square wave, now on the primary side we have shifted to quasi square wave. Okay. So, what is in quasi square wave? It has 3 levels of voltages, positive, negative, and for finite duration it will be 0. Whereas, in the square wave, if you see, it was either positive, it was negative. Okay. So, here we have introduced one more control variable. First was our delta, now other one we can mark it as D1, delta 1 as per our requirement. Okay. So, we have 2 degrees of freedom now. I can control the phase shift between V1 and V2 voltage, and in the other side I can control the duty ratio of the voltage V1, or I can increase the 0 duration of this voltage to have an other second variable. Okay. So, here what are the advantages of this method? It can be used to reduce our circulating current. So, by default this method will be having lower circulating current compared to our single phase shift control technique. We have 2 degrees of freedom. Now, I can assign 1 degree of freedom to control the power flow, and other degree of freedom can be used to do some other task, like you are expanding the range of ZVS or reducing your circulating current and those things. Disadvantage, this will not be able to provide as very wide range of operation, because we have many other advanced control techniques which will be giving us more increment in the efficiency. So, here we have now compared to your single phase shift control, we have extended phase shift control where we have moved from 1 degree of freedom to 2 degree of freedom. What was the second degree of freedom which we have introduced? That is our width of this voltage V1. Okay. So, now this method will have one more issue, that is the loss distribution. If you see, the duty ratio or the conduction time of the devices has become unequal for both of my bridges. On the primary side, if I assign the task of Cauchy square wave generation, on the secondary side they are operated with 50% duty ratio, whereas in the primary side they are operated with a less duty ratio. Okay. So, this operation has to be flipped. So, what is the meaning of that? For few, suppose for 10 number of cycles I assign the task of Cauchy square wave to V1. After some time, after 10 cycles I will switch and I will assign the task of generating Cauchy square wave to the V2. Okay, and so on. This can be done by just your control logic. Okay. Then next, if I want more flexibility in the control technique, so we have the other method, that is your dual phase shift control technique. If you see in this case, we have two Cauchy square waves. We are not generating any square wave. Both the bridges are given as Cauchy square wave operation. Now, here in this dual phase shift, this width of the Cauchy square wave is fixed for both the bridges. Okay. So, here also we have 2 degrees of freedom. Okay. So, first degree is the phase shift between your V1 and V2, the second one is your duty ratio of your Cauchy square wave or the on time of your square wave. Okay. So, always they will be placed symmetrically across your time axis, so that we will not get any unwanted harmonics at the transformer terminals. Okay. So, here it will have lower circulating current. So, as the circulating current is decreasing, so efficiency will be high in this case. Demerit wise, from the single phase shift control, obviously we have increased our complexity. Now, we have to calculate delta 1 and delta 2 control parameters online when the circuit is in the operation. Okay. So, we have other methods also, that is triple phase shift and so on. Based on the application, we can choose any one of the control technique to have the required design parameters as per the application. So, with this we will stop our discussion on our dual active bridge or the DC to DC converters. Now, we have seen this part, DC to DC converter till now. Okay. So, we will now shift to this stage, that is our AC to DC conversion stage. Okay. And we will see what is the requirement of power factor correction circuit over here. Okay. So, and the other use of our AC to DC converter will be on board before the electric motor. Okay. So, inside the vehicle also we will have this AC to DC converter, but they will be mostly on the 3-phase architecture. First we will go with the single phase. So, we will be concentrating on this part mainly for the next few slides. Then we will shift to this onboard 3-phase AC to DC converters. Okay. So, now we will discuss about our AC to DC converters which will be used in our EV circuits. Okay. And we will see what is the requirement of this power factor correction circuit. Okay. Now, AC to DC conversion. So, here why we require this stage? Always most of our input to our home or the charging stations, they will be on AC. Okay. So, if we are having AC, but our charger requires DC output because we have a battery bank which has to be charged. So, we have to convert this AC signal into DC. Okay. So, what is the best option available with us? So, the cheapest and the simplest option available with us is your diode bridge rectifier. Okay. So, what will be the operation of this diode bridge rectifier? We have an AC voltage over here. Okay. So, now let us consider this terminal for the positive half cycle, that is during this period I have positive voltage over here, negative voltage over here. Okay. So, now let us see which diodes are forward bias and which are reverse bias. So, we will mark this as D1, D2, D3, D4. Okay. So, if this terminal is positive, then which one will be positive bias? So, D1 will be positive bias, D2 will be reverse bias. Why? We have positive terminal of the supply across D2, so it will not conduct. So, this can conduct, whereas on this leg if I see we have negative terminal over here. So, D4 can conduct, D3 will not conduct. Why? The positive side is connected to the negative of supply. So, what will be the V0 voltage in the positive half cycle? As my diode D1 is conducting, so this positive terminal will be over here, this negative terminal will be over here. So, for this first half cycle, this terminal is generally considered as positive, the upper one will be positive. So, positive is connected to the positive. So, I will get positive output voltage. Okay. So, what happens in the negative half cycle? As we have an AC supply, so it will be bidirectional, that is it will be having positive and negative instantaneous polarities. Now, in this case, this terminal will become positive, this terminal will become negative during this stage 2 or our negative half cycle. Okay. So, in this negative half cycle, this terminal will be now positive and the other one will be negative. So, now which diodes are forward bias? If I see this is reverse bias, so D1 cannot conduct because the negative side of the supply is connected to the positive of your diode D1. So, it is reverse bias, whereas in D2 it is forward bias. In this case, this is reverse bias. Why? D4, if you see, the negative side of the diode is connected to the positive of the supply, whereas D3 is forward bias. Now, this D2 and D3 will be conducting for the negative half cycle, and if I see this positive terminal is again connected at this point. Okay. So, the output is again positive. Okay. Although my supply has flipped its polarity because of the bridge operation or because of the diodes operation, we have seen that the output will be always maintained positive and we will get this rectified sine wave. We call this shape as here rectified sine wave. Now, what will be your load current? Suppose I have resistance at the output. For simple illustration, we will consider an resistive load over here with R resistance. So, then we will get an rectified sine wave at the output stage. Okay. So, its magnitude will depend on now V0 by R or the resistance value. Based on that, this amplitude will be changing, but the shape will be your rectified sine wave. Okay. Now, what are the conclusions from this one? Output voltage is uncontrolled. Why? The moment, suppose this is connected to a single phase household supply whose RMS value will be 330 volts, or I can say that 311 at the peak value. So, if this is fixed at 230 volts, then my rectified voltage is also fixed. The shape of this one or the amplitude of this one will be fixed at 311, and the average value, if I calculate the DC value of this one, it will also be fixed. Now, it depends only on the input voltage. Okay. If I want to regulate the voltage V0, suppose I want variable V0, what option is available with me? As such, in the circuit, there is no control option available because they are diodes, they do not have any control terminals. So, I have to either connect an auto transformer at this stage or somehow I have to vary the input voltage. Okay. So, there is no, as such, there is no default control directly to regulate your output voltage. Once the input voltage is fixed, the output voltage will be fixed. So, output voltage is not constant DC. Okay. So, although the average value is fixed over here, if I calculate the average value is fixed, but instantaneous values, if I see the error, so if this is the error average value, so during the zero crossing the error is very high. So, it is not constant. What is a perfect DC? It should be constant, its amplitude should be constant. The dotted line, if we get the dotted line as our output voltage, we say that it is an perfect DC, whereas in this case we have high amount of ripple percentage. The power is delivered in the both the half cycles because of the alternate in operation of the diodes. The power flow is continuous, that is it is conducting for both negative and positive half cycle of the AC supply. Now, suppose I want an constant output voltage, I am not happy with the high percentage of ripple, which is generally an undesirable condition. So, we will have an we will try to connect an capacitor at the output stage. The best component to reduce your harmonics on the voltage is your capacitor. So, we will connect an capacitor at the output stage. Now, what will happen in this condition? Suppose we assume that we had this 230 volt supply, which will be having a peak, let us say around B peak is around 311 volts, and we have a capacitor in this stage. Okay. So, will the operation be the same as we have discussed in the previous case? The answer is no. Now, why? This capacitor will be retaining some voltage. Suppose it is charged to 200 volts. Okay. So, it is at 200 volts. Now, we have 311 as our supply peak. The source voltage RMS is 230. Okay. So, now when can the diode conduct? Suppose I have just crossed 0. Okay. and this terminal is positive, this terminal is negative. What was our previous inference? D1 will be conducting and D4 will be conducting because they are forward bias. But in this case, suppose it has just crossed 0 and my input voltage, instantaneous input voltage is 10 volts. Okay. So, in the positive half cycle we were somewhere here, okay. So, where the voltage is very low, it is around 10 volts, and the capacitor, suppose it is charged to 200 volts. Okay. So, now what will happen? The plus 200 is over here and the ground is over here. Okay. So, if this plus 200 is there, now let us see, D1 was supposed to conduct. So, if I see this potential, it is at 200, whereas this potential is at 10 volts. So, they will be reverse bias. So, it will not be able to carry the current. Okay. Similarly, when I go for the other diode also, I will see that they will be not be able to carry the current. But will it be true for the entire positive half cycle? No. Slowly, because we have an AC supply, so it slowly amplitude will be increasing when we travel towards 90 degrees. Okay. Suppose at this point, at this instant, okay, the voltage has now increased, instantaneous voltage instead of 10 volt, it has gone to 10 volts. Okay. So, now what will happen over here? We have positive side on the 10 volt and then negative side of diode D1 at 200 volts. So, obviously, and positive 10 volt is applied across this diode. So, it can conduct. So, it will start conducting when my capacitor voltage is less than the supply voltage. Okay. Suppose let us assume this is my capacitor voltage. Okay. So, where it can conduct? In the previous case, what was our waveform? This was our waveform. Now, at what stage it can conduct? Only when my input voltage crosses this capacitor charge voltage. Okay. So, it will be conducting for this duration. Again, your capacitor, it will not be in straight line, it will be slightly slopey because your capacitor will be discharging during this time, and it so on. Okay. So, let us remodel this one. It will be bit discharging, drop in slope. Okay. Then again over here it will start from this point and continue the conduction. Okay. So, what has happened now? As my capacitor voltage is increasing, the time given for my diodes to conduct will be decreasing, because it will wait till it gets closer and closer to 90 degrees. More is the voltage, it will wait for more time till it becomes positive bias and it will start conducting. And in such case, what will happen to the current which will be drawn from the source side? Okay. So, now in this case over here, this current, this part, the current was flowing from the capacitor. Okay. Now, in this stage the current will be drawn to feed your load as well as to charge your capacitor. Okay. So, on the output side, this waveform divided by R, that will be my current profile, whereas the source current, what will happen to the source current? Now, the source current which will be drawn, it will be used for two tasks. First is to charge your capacitor and second is to supply your load. Okay. So, your source, whenever it gets the diode in the conduction mode, it will try to charge the capacitor as well as feed the load. Okay. So, in such case, what will happen to my source current? So, your capacitor is getting a small time period to charge itself, because your capacitor is not a permanent source of energy, it is not an active component, it is a passive component, it can just store energy and give for a small duration of time. So, the moment it starts feeding the energy to the load, its voltage will be decreasing. So, it will, if we want steady state operation, it has to equally charge and discharge. So, it has been given, suppose this is an example where it has got small duration to charge itself. Okay. So, what is the meaning of that? It is charging during across this duration. Okay. So, this for this duration it is charging. Okay. So, it gets forward bias over here. Again, the when the supply voltage gets below the capacitor voltage, diodes get reverse bias. So, they stop conducting. So, your source current will become peaky in nature. Okay. Because in this small duration, the entire load power plus the power which will be stored inside your capacitor, those will be drawn during this small time. So, your current will become peaky, and when I go for Fourier series expansion of this one, I will observe that it contains huge amount of harmonics and the power factor will be very low. What is the meaning of low power factor? Most of the currents which will be drawn will be having reactive component rather than the active component. We want the power factor to be nearby unity, such that only active power is drawn from the supply and or useful power is drawn from the supply, reactive power is minimum. Okay. So, here advantage wise, now your output voltage can get regulated. Okay. Why? Because in the previous case it was having sinusoidal voltage. Now, here in this case, because of presence of the capacitor, the distortion has become less or if I calculate the percentage of ripple in the previous case and in this case, obviously the ripple percentage is very less, because it is subject to the variation in the capacitor voltage only. Okay. So, the output voltage gets regulated in terms of your harmonic performance. Then the supply current gets distorted. Why? We have given a small duration of time during which your source is able to feed into the load and charge the capacitor. So, it will be becoming spiky. So, it has huge amount of harmonics. So, we say that to be distorted. Okay. The output voltage side, we have got and flexibility of regulating it. It was not going to 0 as in the previous case. So, the harmonic percentage has reduced, but we are not able to address the issue on the source side. This side the power factor has become very low. So, this is this reason why we require a power factor correction circuit. Okay. Because if I connect these charges, we will be drawing huge amount of reactive power. So, they will be creating a huge issue on the grid system. Okay. So, when we have grid, so this harmonics will be drawn from the grid and it will be creating a huge issue. And when we go for commercial charges, which will not be at our domestic terminals. Okay. So, in our household supplies, we are never concerned about the power factors, but for the commercial applications, we should make sure that we are not drawing huge amount of harmonics from the source. Okay. So, that will be the system operator's requirement. We have to maintain the power factor of our load for commercial usage. Okay. So, now here what are the advantage of this case? The output voltage has nearly become constant. Okay. So, in the previous case it was rectified sine wave, where the moment we have capacitor in between. So, the output voltage ripple has decreased. So, now we can consider that to be nearly constant, neglecting the small amount of ripple. Okay. So, the power factor or the current which is drawn from the supply is highly distorted. So, it is having huge amount of reactive power. So, it is non-unity power factor. It has high amount of TSD, or harmonics are very high. The source current is peaky. Instead of sinusoidal current which we require from an AC supply, we are drawing peaky current. Okay. The circuit component has to be oversized. Why? The current rating and the voltage rating are defined by the maximum voltage and currents they have to withstand. Okay. So, here they will be oversized because they have to withstand this peaky nature of the current waveform. Okay. Now, thus to regulate the output voltage, that is both to have your controlled voltage as well as to have your better power factor on the source side. So, we want this to be having an unity power factor. The current which is drawn should be in phase with our. So, what is unit power factor? If this is the voltage, if the current is in phase with our supply voltage, we say that to be at unity power factor, or we are drawing only the active power factor. Okay. So, to address these two challenges, to regulate the output voltage or to have minimum DC ripple and to have better power factor on the supply side, we will be requiring an intermediate stage, that will be our power factor correction circuit. Okay. So, now this power factor correction circuit will be an converter. Okay. So, we will see what will be the simplest option available with us, that is our boost power factor correction circuit. Okay. So, if you neglect this one, if you replace this as an DC source on the output stage, if you see this part of the circuit is nothing but similar to an boost circuit which we have discussed. Okay. So, now we are using this boost circuit to regulate the current which will be drawn from this side. We want the source power factor to be nearly unity. Now, in this case what will be done? Now, here we have this switch. Okay. So, I can control it, turn it on and turn it off. Beforehand we had only diodes where we did not have any control terminals. Because of that, we were not able to change the output voltage until and unless we were changing the input voltage. Okay. So, here we have capacitor. Okay. So, assuming the capacitor is properly designed to regulate the voltage around the reference value. Okay. So, the mid point of this graph will be my DC value. Okay. So, now what happens when the switch is closed? What is the voltage over here? Can I write it like mode of Vs, if this is Vs? Yes. Why? We have seen the operation of our diode bridge, it rectifies the supply voltage. Okay. So, we will get mode of Vs, we have L over here, we have switch 1, we have diode. Okay. So, now what will be the operation of this converter? When I close switch S1, what will the voltage across the inductor? Now, in the previous case, in the normal boost converter, it was connected across the supply voltage. In this case, it will be connected across the mode Vs. Okay, so mode Vs is not a constant one, it is a variable, but as it is mode Vs, it will always be positive. So inductor will be charging. Okay, the moment I disconnect the switch, your inductor was having some energy, so it will force the current through this circuit and it will charge the capacitor and the load. Okay, the operation of your boost converter remains the same. Only thing is, on the supply side, we have replace the constant DC by your absolute value of your sine wave because of the presence of your diode bridge converter. Okay. So, when the switch is closed, so it is experiencing this inductor current, whichever will be drawn, that will be drawn from this side. Okay. Why? The switch is closed, so it has to see the source current which has to be flown through the inductor, because source and your inductor will be coming in series when the switch S1 is closed. Okay. So, based on if you are in the positive half cycle, these two devices will be in the conduction mode. When we are in the negative half cycle, the other two devices will be in the conduction mode, but this IL will be drawn from the source, okay, irrespective of the positive or negative half cycle. When this switch is closed, okay, so what will happen now? Your source current will slowly increase. Okay, let us assume that we have an band over here. Okay, so what is the meaning of this band? We will see that. Okay, so at this point, it starts. At the moment I close it, it starts charging. Okay, so after it reaches this point, by sensing current, suppose I disconnect that. Okay, so what is the meaning of disconnecting? I am removing the pulse from S1. So it will discharge and it will feed the capacitor as well as the load. Okay, the inductor, whichever energy was stored inside it, it will be given to the output stage of this converter. Okay, then it will start discharging. The moment it touches the lower band, suppose I again turn on the switch, again it will be connected across the Vs. So, it will be charging, again it will be disconnected, discharging, charging, discharging, and so on. Okay. So, for our better visualization, we have considered an higher bandwidth. Okay, so this band will be having a very small width. Okay, so we will see what is the importance of this band. So, I can now turn on and turn off to follow this sinusoidal trajectory on the input current. Okay, so what is this input current? It is nothing but, this graph is nothing but your IL. Okay, so unfolded version of your IL will be flowing through your source. Okay, so the why unfolded version? Because of the presence of diode bridge rectifier over here. Okay, so if I reduce the band now, okay, suppose I am not happy with that higher band, I will reduce it to smaller band value. Okay, now what will happen over here? It will start charging, discharging, charging, discharging, charging, discharging, and so on. Okay, so lesser is your band, more sinusoidal will be the current which is drawn from the source. Okay, so what is the demerit which you will get by reducing the band? Okay, so the more is the width, more will be the deviation from the sine wave. Okay, less is the bandwidth, more sinusoidal will be the current which will be drawn from the source, but the switching frequency will be increasing. Okay, so based on my harmonic performance requirement, how much closer to sinusoidal is my requirement, and based on the switch available with me, so I will be deciding what will be the band and what will be the operation of this converter. Okay, so more or less it should be clear now. So when my switch is closed, mode Vs is applied across the inductor. Okay, so it gets charged. When I disconnect the switch, because inductor was having some energy, so now here it will be experiencing the voltage difference, that is mode Vs minus mode output voltage is DC, so it will be mode Vs minus Vo. Okay, so this will be applied when the switch is open or it is off. Okay, so when the switch is open, so it will be experiencing the difference between the input and output voltage. When the switch is closed, it will experience the source voltage. Okay, so now here obviously the switching frequency of the converter will be much higher than your supply frequency. Okay, so what is the supply frequency? In Indian it is grid, it is 50 hertz. Okay, or the other option available is 60 hertz. Okay, so 50 or 60 hertz, whereas the switching frequency will be much higher, it will be in the kilohertz range. Okay, so this switching frequency will be very high, so that's why we will get high percentage of this on and off cycles. Okay, so one switching frequency will be, or one switching cycle will be equal to one pulse over here. Okay, or one charging and discharging cycle of the inductor L. Okay, So, more is my switching frequency, more will be the efficiency of tracking the sine wave. Okay. So, the input current will be more and more sinusoidal by increasing the frequency based on the switch capacity and the heat sink and the cost of the converter which we are designing, we will fix the maximum switching frequency which can be given to this. Okay. So, now let us see various waveforms. Okay. So, when the switch was on, it was experiencing the supply voltage. Okay. So, we have considered a small duration. Now, although we have the supply voltage as sinusoidal in nature, we are considering one switching time period. Okay. So, as I said, the switching time period is much higher than the supply frequency. I am assuming that for one switching time period, the source voltage is constant. Okay. So, that is how we have got this waveform. Okay. So, we are seeing just one switching time period. Okay. In that, I can assume the sine wave to be constant because the switching frequency is very high. So, what will be this Vs minus V naught? When the switch is open or when it is disconnected, it will be experiencing the difference between my input and output voltage, because on one side input is connected, on other side VO is connected when the switch is disconnected. Okay. So, the inductor will experience Vs minus VO when the switch is off. Okay. So, in this case, in the first case, it will charge. Okay. So, when obviously over here the supply voltage is applied across the inductor, this is the loop which will be formed. Okay. So, your inductor is experiencing positive voltage across it. So, it will be charged. Okay. So, it will be always be experiencing positive voltage because we have diode bridge over here. Okay. So, it is mod Vs. So, we are considering only on switching time period. So, in this case it experiences a positive voltage. So, it will experience rise in the current. When the switch is off, it will experience decrement in the current. Okay. Now, here if you see the charging and discharging durations are not same. Okay. So, why it is so? Because the supply voltage itself is a variable one. Okay. The moment we go into the next sample, we will see that some other value of Vs has come into picture, because it is an rectified sine wave mode of Vs. At this point, we get rectified sine wave as our input voltage to the boost converter. Okay. So, it will be for the entire cycle, if I see, it will be tracking an sinusoidal reference. Okay. So, over here if I measure it, it will be mode of Is here, which is Is. Okay. Because of the presence of diode bridge, the current will also get rectified. Okay. Now, here switch 1 current, what will be the switch 1 current? Whenever we have this in the on state, then the current is flowing through the switch. When it is becoming off, it flows to the diode. So, for 0 to dt time, that is my on time of switch 1, it will carry the current which will be equal to your mode of Is or the rectified version of your source current. Okay. So, in this case the duty ratio will be variable. Okay. So, why the duty ratio becomes variable? Because now the input voltage is variable. Okay. Near the 0 voltage crossing. Okay. So, if we have suppose just entered into a positive half cycle and we have got 10 volts at the input. So, it will take an higher time to charge. Why? The moment I close the switch, what will the voltage which will be applied across the inductor? It will experience 10 volt, which is my supply voltage. Okay. Suppose I am nearby 90 degrees where we have this 210 volts at the input voltage. Now, if I close the switch, 210 volts will be applied across the inductor. Okay. So, its slope will be decided by this input voltage, that is 210 volts. So, it will be higher, or the rate of charge change of current will be higher, or the slope of the line will be higher when we are at the peak value. It will be less, or the charging slope or the charging rate will be less when we are at the 0 crossing. So, the duty ratio will now become variable. It will depend on at what point of the sine wave we are operating the converter. Okay. The duty ratio becomes variable. Now, based on my requirement, that is the source current to be sinusoidal, I will calculate the duty ratio. Okay. So, we will see how this duty ratio is calculated. So, now for the calculating the duty ratio, we will follow the same procedure that we will go for your volt second balance. Here 0 to T by 2 duration. Okay. So, we are integrating it. Okay. So, for the dt time, the switch on time. Okay. So, here why we have replaced d with d of t? Because now d of t is also an variable with respect to time. Okay. So, in our DC to DC converter stage, this duty ratio was fixed based on the input and output voltage. Okay. But over here, because the sinusoidal nature, we will be having the duty ratio dependent on the period of the cycle or the time at which we are at the cycle. Okay. So, near the 0 crossing and at the peak values, the duty ratio will be very different. Okay. So, here when the switch is on, mode of Vs is applied. When the switch is off, that is 1 minus dt time, it is experiencing the voltage which is equal to difference between the input and output voltage. That is how it has been written. Okay, it is the same equation which we have seen for our normal boost converter. Only thing which has changed is now we have mode of Vs instead of an constant DC voltage, we have an variable duty ratio instead of an fixed duty ratio in our previous analysis. Okay. So, when I solve this, I will find out that the duty ratio will be 1 minus mod Vs by V naught. Okay. In our previous case, for our boost converter, what was our duty ratio? The relation between your input and output voltage was equal to V0 was equal to your Vs by 1 minus D. Now, here we have got an variable. Why? Because this is your sine wave. Okay. So, what will be the variable which will be present inside it? It is V peak sine omega t. Okay. So, now this voltage has become variable. So, our duty ratio will also be an variable. Okay. Now, let us see what will be the dt, the variation in the duty ratio over an cycle. Okay. Assuming we require the output voltage to be constant. Okay. So, now this is mod of Vs. Now, this will be my duty ratio. Okay. So, if you see near the 0 crossing, okay, so near the supply voltage is 0. Suppose if I replace it 0, what will be my duty ratio? It will become equal to 1. Okay. So, now near the peak value, what will be the relation over here? So, output voltage, it will be somewhat higher. Suppose it is 350, the peak is now at 311. Okay. So, what will be the duty ratio? It will be nearby 0. Okay. So, it will be maximum at the 0 crossing, that will be, it will be close by 1 at the 0 crossing, and at the peak value it will be nearly 0. Okay. So, why we have connected boost converter over here? Why can't we go for the other converters? Okay. So, here if you see, we have marked this as 350 volts. Okay. Why? If I want to have steady state operation, can I have, suppose for example, I have 200 volts over here by mistake. Okay. So, we have 311 volt over here. Can this converter operate? The answer is no. Why? During the peak values, it will charge. When I disconnect it during this time, if this is 311 and this is 200, again your inductor will experience a positive voltage, it will never get discharged. Okay. So, to ensure that this inductor gets discharged when the switch is off, the output voltage should be higher. So, we always have an boost converter in between. Okay. So, what will be the duty ratio? Near the 0 crossing, it will be nearly 1. At the peak value, it will be having the minimum value based on the relation between, or how much difference is there between the input and output voltage. It will be somewhat nearby 0. This will be a very small value. Okay. Why this will be a small value? On the other side, if you see the mode of your Vs, that is your supply voltage is higher, so your rate of charging will be higher. So, for it within small time, your inductor will be charging from your lower band to the upper band, or the current will be increased from the lower band to upper band. So, your duty ratio can be minimum at the peak values, whereas at the 0 it will take a longer time to charge. So, your duty ratio will be nearby 1. Okay. Now, let us see what will be the change in the inductor design in this case. So, till now what we have seen, we have first discussed about the various modes of operation of your DAB. Then we have seen our diode bridge rectifier, and we have seen what is the requirement of power factor correction circuit in the diode in cascade with our diode bridge rectifier to improve the performance of the converter. If I want the current to be nearly unity, I have to connect an power factor correction circuit in between. Okay, or else the power factor will be very less when we have a diode bridge, and on the output stage we have capacitor, or we have for our charging application, if we have the capacitor instead of capacitor we have the battery bank, we will have similar type of observation. The current will become peaky and the power factor will be very poor. So, we will have an power factor correction circuit in between. The first example which we have considered over here is our Boost PFC. It is the simplest power factor correction circuit. We have seen the duty ratio variation and how it is related to your input voltage. We will continue with our discussion and design the inductor in our next session. Thank you.